let us start this lecture with a thought process that your deadliest envy is the best friend who compels you to realize your potential while soiling his own soul. All the time we will be worried about enemies, but they are your friends. So, let us recall what we learned in the last lecture. We basically looking at how to handle the mass burning rate of the droplet under convective environment, and we looked at basically heat balance at the surface of it and then trying to look at it. It is a very you can say ad hoc solution. So, rearranging the earlier equation, we can get basically SC Rs by kg, and this is ln 1 plus V, and these terms you already we had discussed last time. So, if you look at this is nothing but your Nusselt number based on the radius at the surface, radius of the droplet, right. And if you look at this term is nothing but your, it is basically B, right. And so, therefore, I can get nu Rs is basically ln 1 plus B divided by B. B is the transfer number. For combustion we can write C basically, for evaporation it will be different, right. And this is basically what we have looked at is some kind of a simplified way of looking at it. It does not include the Reynolds number or the Prandtl number, although this will be valid for that what we have seen, right. So, for high Reynolds number we can plug in some of the relation from the heat transfer to into this, right, and develop a semi empirical relation which has been proposed as nu ln 1 plus B divided by B, and as I told this you can say combustion 1 plus 0.39 Prandtl number power to 0.33 and RES Reynolds number based on the RS power to the 0.5, and this you might have familiar with these things, right. This is generally valid, what you call it, mimics the experimental data well. So, for the force convection is concerned, this is for the force convection, right. And if you want to deal with basically natural convection, you can express in terms of Grashof number, right, and we will be not discussing about that. And now, if I say that this Reynolds number is much larger than the Prandtl number, right, and then you will see that this expression can be simplified further. That is, I can write down ln 1 plus BC divided by BC plus 0.39 Prandtl number 0.33 RERS 0.5 and ln 1 plus BC divided by BC, right. And if you look at the first term here, this will be quite small as compared to second term, right. Why it is so? Because if you look at it is ln, and then this is very small, and this will be quite small, right. Right. I will take an example. So, let us see that if B is 7, for example, B value is 7, then what will be ln, let us say BC, BC plus 1 divided by C, that will be 0.29. Well, let us take another example, BC is basically 2. So, then this term will be ln BC plus 1 by BC will be very small again 36, right, because this is a logarithm term. So, therefore, it get compressed and then very small. So, therefore, this is small, you can neglect it, and if you neglect that one, So, you will also say that this will be equal to 1, it is not really. So, you will get NURS is approximately equal to this one, right. You can use this provided the Prandtl number is equal to 1. A Prandtl number is very, very small, right, and so you can see. Now, what we will do, we will basically look at this expressions, right, and see that derive some relationship for mass burning rate for convective environment, right. So, let us derive an expression for the mass burning field in convective environment as, see, we know this NURS, we are taking this relationship here, right, HCRS by Kg is nothing but ln 1 plus B divided by B. Keep in mind I am just using sometimes B, sometimes BC, but it is C stand for combustion. 1 plus 0.9 sorry 1 plus 0.39 Prandtl number power to 0.33 Reynolds number power to the 0.5. So, let us look at certain things and then find out like how we can relate. For example, if you look at this SC RS by Kg, right, already we have done, right, and this is your Nusselt number basically, right, and that is what delta T, SC is your convective heat transfer coefficient, RS divided by delta T Kg. We are just putting delta T here and delta T there, that is all you are doing. And in place of this, we know that delta T SC is nothing but your rho S V S delta H V, right. So, I can in place of this I can use this one, right. We have already done that, and rho S V S delta H V R S, and I am just multiplying Cp in the numerator and Cp in the denominator, and delta T remains same, right. And keep in mind that what is this term? This is basically mass flux of fuel, right, of course with convection, right, that we are considering because Nusselt number is there. So, there from that we can find it out, right. And if that is the case, I can write down that as basically as convection and RS, right, and delta H B by I can say Cp delta T, because this is delta T I am taking, into Cp by Kg. I am just rewriting these terms, right. And keep in mind that this Cp delta T divided by delta Hb is what? What is that? That already we have done, that is basically Cp, we know that Cp delta T by delta Hv is equal to Cp F y oxidizer infinity delta Sc divided by Cp, right, plus T infinity minus Ts and 1 over delta Sv, right. This for delta T I can write it down, right. So, therefore, I can now club this this relationship. Let us say I can say this is equation 1 and this is equation 2. I can, because both are same, both are basically no sorry, this is not the case, this is the case, okay, this is the case, and I can write down here, this one, and let us say this is 3, right. And I can use equation 1, 2 and 3, I can write it down as basically F convection is basically if you look at, right, this is nothing but your B, right. Okay, let me write it down. This is, I have already written down RS, this is delta H V by Cp delta T, Cp by Kg, I am rewriting, right, and this Cp by delta T is nothing but your, this is 1 over B, right. I can write down m dot F convection RS is nothing but 1 over B, and Cp by Kg is equal to, what is that? That is basically ln 1 plus B divided by B into 1 plus 0.39, Prandtl number 0.3, Re Rs 0.5. So, this will cancel it out and you can get basically a relationship which will be convection is equal to, right, is equal to Kg, I can take to this side Kg by Cp and Rs, and then rest of the terms, right, that is ln 1 plus B 1 plus 0.39, Prandtl number 0.33, Re Rs 0.5. And now this is a very nice term for convection. If you look at, it contains all the terms, right, both Reynolds number and other things. I can say this is equation 4. Now, if Reynolds number is 0, that means it is basically quiescent atmosphere and the what do you call 0 G, then for Re Rs is equal to 0, right, then equation 4 becomes m dot F G is equal to 0, is Kg by Cp Rs ln 1 plus B 1 plus 0.39, Prandtl number 0.33, Rs 0.5. So, this will be 0. So, then this will be basically Kg by Cp Rs ln 1 plus B, right. This is equation 5. Dividing equation 4 by equation 5, we can have m dot F convection divided by F G is equal to 0 is equal to very simple term, that is 1 plus 0.39, Prandtl number 0.33, Re Rs 0.5, that is all, where this term will be cancelled it out. And this is a very simple expression which is quite elegant in nature, right. And keep in mind that because of convection, this mass burning rate will be increased. Generally people get this mass burning rate with convection gets enhanced from around 20 to 40% as compared to a quiescent case. In other words, the convection plays a very important role for enhancing the mass burning rate, and which is of course the obvious thing, and that is being derived here. So, if you look at, you can use this thing expression for solving these problems, and keep in mind that these are not very accurate. Okay. But however, it can be used for design purposes, because it is not available. So, naturally you can use it. So, and it will not be very accurate because of fact that, right, this wake region is not being taken care by this analysis, right. So, therefore, it will be not right, and wake will be changed depending on how it is. So, this for laminar and then turbulent, all those things will be. And very interestingly, if you find out the d square law, you will find out for a force convection laminar droplet burning rate follows by d power to 3 by 2 as compared to d square in case of quiescent atmosphere. This is something 1.5, and that is 2. And if we enhance the turbulence level, then it will be 1. Are you getting? So, it became almost linear, the changes in the droplet burning time or droplet lifetime, that you can say. So, with this we will look at, we have looked at how to take care this droplet combustion in a convective environment. Now, we will be looking at basically how we will do in a handle the spray combustion in a very simplified way. We will be using a simple spray combustion model. You assume that this is a one dimensional tube, okay, and of course, it is a circular, it is only varying along the x direction. Keep in mind that this injector or the atomizer, right, this is the atomizer, is a fuel atomizer, right, is far away from this x position where we are looking at the thing, and it says that it is good enough such that the monodispersed droplets are available. And keep in mind that monodispersed droplet really is not possible to have it unless you produce in the lab in a controlled conditions, right. But however, for simplicity we are considering. So, we will be making certain assumption before carrying out the analysis. One is steady one dimensional laminar inviscid flow, right, and that we do all the time. And the monodispersed droplet, as I told, monodispersed means the droplet size distribution will be same, right, and that is the condition. And of course, you can extend this for the polydispersed droplet, but that will be quite complex, and pressure remains constant along the x direction during combustion or along the length of the combustors, right, which is shown here, and that we have already done several times. So, this is not a bad assumption as such, and droplets move with the same velocity as that of the air, because the the velocity here at this location, this is basically 0, and the velocity will be v naught. This is the mixture velocities, right, fluid will be moving, and there is no lagging or the relative velocity between the droplet and this thing, because what happened if it is v naught here, right, and droplet may not move at the same velocity, but in this case what we are saying, it is also moving with v naught. That is the assumption we are making. That means there is no difference, okay. But in real situation it will not be, never. Of course, if it is a too small droplet, it may possible that it will be the lagging between the droplet and the your fluid will be not there or will be minimum, but okay. So, vaporization and ignition begins at x is equal to 0, this is your x, right. Nothing is happening here, it is just mixing, but actually vaporization can occur here itself once you atomize in the very after this fuel ejected from the orifice of the fuel atomizer, then it can be started vaporizing, right, once it is pumped. But however, we are saying it is still wet this, and that is for the simplification. and mixing and chemical reaction times are as compared to droplet vaporization time, because basically droplet vaporization will take more time because it is governed by the diffusion, right, and chemical reaction is very fast because we will be using all the time the thin flame approximation this, and also this will be diffusion control. So, therefore, this is the valid assumption one can say, and constant thermophysical properties which we will be discussing we will be using there because there is no other way you can handle, and this is a dilute spray, right. Dilute spray means the droplets will be, it is not a dense spray, right. The number of droplets per unit volume will be very less in the case of dilute spray or the number density, and stoichiometric fuel air ratio we are considering. Then we can take this control volume here, right, and we can find out basically this is the fuel air ratio is nothing but your F is equal to mass of fuel divided mass of oxidizer, right, and that can be really derived from here, and by this expression it looks to be quite complex, but keep in mind it is very simple because N naught is the droplet number density, that means number of droplet per unit volume, that is N naught, into rho L is the basically density of liquid fuel, right, and d naught is the initial diameter of droplet, and A I have taken this cross sectional area, and delta x I have taken this control volume. So, you can look at it, and this is basically this portion is mass of F, and this is basically rho naught, keeping density of fuel air mixtures, right, mass of fuel air mixture, fuel plus you can say air, right, or oxidizer, right, oxidizer, and this is the mass of fuel, right, this is your mass of fuel. So, I can write down the basically MF MF is equal to M of A plus oxidizer minus MF, right. So, we can basically it is a very it can be simplified very easily, but however, it has been done in such a way that if there is a distribution you can integrate, right. If there is a variation along the cross sectional area you can integrate also, right, or if there is a variation, right, you can do that, but we will be looking at that. That F I can write down as this, right, and I can write down this as basically F rho naught, right. I can cancel this out, right, this out I can cancel it out, rho naught is equal to N naught rho L I can take out, and pi by 6 d naught q is equal to A plus 1, because I am just multiplying here and taking that out, I will get this expression, right. So, therefore, from this I can get very easily N naught number of droplet per unit volume will be nothing but your is equal to N naught is equal to F divided by 1 plus F rho naught by rho L 6 by pi d q, right. And this is we will be using this expression, I can say this is basically equation 1. Now, what it indicates? It indicates that this is basically number density is a function of F and the initial density of the mixture and density of the fuel and of course, the initial diameter. So, the mass conservation, if you look at, I can this cancel it out, I will get basically V naught average by V is equal to rho by rho naught. But what is this V naught average? This V naught average, right, I can write down, this is the average velocity at x is equal to 0, average velocity of fluid, right. We will stop over here and we will discuss in the next, because it will take more time.